Okay, so let's talk about what we've been doing. So I had a handout because that was something that you guys said you really liked that Mark did, so I'm going to try to be just and so I want us to first think about what the big picture is of what we've been doing, okay? And we're going to do that in the context of the problem that we talked about on Monday. This, well, let's not do context right away, but we'll run it in as we talk about it. So, big picture, what have you been trying to do since the end of test 2? So what have we been trying to do? Yes. All right, so we have been trying desperately to find the exact rate of change function given an exact accumulation function. So the way I just said that is the reverse of the way it was written on the paper, right? So given an exact accumulation function, we wish to find the exact rate of change function. Okay? How do we do that? So I gave you a funny look just now. Whoops, I need to practice that before I interview you guys. Okay, so you start with an exact accumulation. So let's go ahead and work with a visual aid while we do this, okay? So we start with an exact accumulation function. All right, so from Monday we had an area function, a of x, that took in a side length, and it outputs the corresponding area of your square with that side length, right? So we started with the exact area. And then what do we have to do? If my end goal is an exact rate of change, what's my intermediate steps? Erin? Mm-hmm. Okay, so I'm going to cut you there. Okay, so that's the next step. So we want to create an approximate accumulation function, okay? And that's going to look something like this. Now, a lot goes into doing that, okay? And so I try to break that down in these steps, okay? So in order to do that, what kinds of things do we have to do? First of all, what type of function are we looking at when we look at this red approximate accumulation function? It's piecewise linear, okay? All right, so there's pieces to it. Well, anytime I start talking about a piecewise linear function, I'm automatically discussing a partition of what? The x-axis, right? I have to partition the x-axis. I have to decide what two things when I create a partition. Beautiful. I have to decide where I start, and I have to decide how big the intervals are. So those are things that are automatically done the second we start talking about an approximate blank function, okay, an approximate rate of change function or an approximate accumulation function. These are decisions that we have to make, okay? Now, okay, so here's the tricky thing though, okay? In order to create my approximate accumulation function that is piecewise linear, I have to write a linear function. What do you need in order to write a linear function? So I heard point and the associated constant rate of change, right? So in order to create our linear pieces, we need the rate of change, right, for each interval. How do we get the rate of change for each interval? Okay, so the rate of change, our constant rate of change, comes from looking at the change in y over the change in x, right? This is the whole shebang. Remember, I told you it wasn't going to go away. Changes in y relative to changes in x. And the idea is that when we have that we want it to be constant, okay? And so, in order to break that down, right, we're calling this thing that we're doing, we're going to call the rates within each interval, okay? We're going to define a function that will produce those for us, okay? So, oh, I gave it away. Shoot, it's right here, right? Okay, so this rate function, can somebody explain to me how it works and how this relates to what I've got written, delta y over delta x? What's the relationship between this function rule and this thing that I have written over here? Do you need to talk to a neighbor about it? Do you have an answer? Because all I hear is the static from the machine. Mm-hmm. Okay, so they mean the same thing. How can you see that the stuff like this f of left of x plus delta x minus f of left of x, how is this showing me a change in y? Yes?
It's showing it's basically kind of like the f left of x plus delta x is basically your ending point on the delta y, and the
Okay.
f left of x is basically your starting point.
Okay, so if I were to pick an interval and highlight a representative interval, right, then the change in y would be represented by this vertical line segment, right? And the highest value, or the biggest value here would be f of left of x, left of x plus delta x, right? And then the lowest y value would be f of left of x. Okay? And then that's over some interval of length delta x. Okay? So that's where that's coming from. Now, we did talk about, however, that when I let delta x get really small, the difference between left of x and x itself becomes irrelevant. Okay? So what we can do is, rather than use left of x plus delta x, when delta x becomes teeny tiny, that difference between left of x and x itself, minimal. So we could simplify our expression to get the rate as just f of x plus delta x minus f of x over delta x. Okay? Yes. So what I want you to visualize is as I let delta x get really small, okay, so let's keep track, well, I can't because my delta x's are going to change. So keep track of, think of, for a current x value, so let's say current x value of 1, whoops, okay. Currently, with the settings as they are, left of x is somewhere over here, right? But what I want you to pay attention to is what happens when I change delta x to be small. How does left of x compare to x itself? Okay, so what's happening? We can't even see it anymore, right? But even over here, like right around there, so x is here, and left of x is like even closer. It's sort of where my hand is right now, right? So the difference between these values becomes minimal to a point where we don't need to pay attention to them anymore. Okay? That's a big deal. Okay? Now, things that we can do is if you flip over your page, we can actually do some computations. Actually, let's not do that right now. Let's, sorry. I promise I thought about this a lot and how I was going to do this. So what we can do then is for this particular function. Oh, question?
Just stepping back
yes.
a little bit. So the piecewise linear
yes.
graph, how exactly does graph calculator generate that? Because I know when we made the first one, we had used a summation notation and the RJ value for each piece. But how does it do that without doing that step?
So you're thinking about when we built from rate of change to accumulation, we had to go through this summation notation.
Right, so that it builds the piecewise or the piecewise linear function, but how do you get that with just one value of L of x?
Okay, so yeah, so let's think about this. So this L of x equation that I've highlighted describes the piecewise linear function that is in red right now, okay? And so how does that one line encode a whole bunch of pieces? And why don't we need the summation notation, okay? So the thing to remember is, what does everything mean? Okay, so first of all, we're starting with an accumulation function, okay? And so my goal right now is just to approximate it using linear pieces, okay? So I already know right away I want to describe linear functions and what is required of that. And so the linear function, though, should still be inputting a current x value and outputting an approximate accumulation. Okay, so the things that I want to get out of it are accumulations. So let's look and see, what does the pieces within this function represent? Well, if I look at this, that's an f of left of x, right? So f here is my accumulation function. Okay, so it's outputting some bit of accumulation, right? And then if I look at this piece over here, it's composed of a rate times a little bit of change in x. So when you get a rate times a little bit of change in x, that gives you what kind of thing? It gives you the little bit of accumulation corresponding to that change in x. Okay, so we're adding a little bit of accumulation to the accumulation up to left of x. So this piece right here is actually, it corresponds to that summation over the complete intervals, that whole big messy thing, right? This notation by itself represents that whole summing up of the complete intervals up until the left end point of the current interval. And then this piece is saying within the current interval, here's the change in x, and here's the rate of change associated to that interval. So here's the little piece of accumulation, okay, that we had right when we did. So the order is reversed, if you will, from when we built rate to accumulation. We had our total accumulation from the intervals, from the complete intervals. That's now represented just with this powerful little piece.
I guess I just don't understand how that happened.
Well, so f itself produces the accumulation up to the input value, right? And so when we say, tell me the accumulation up to left of x, okay, we're saying I've partitioned, so let's say we started at 0, and I've partitioned my x-axis, right? And this black blob is my current value of x. When I say, tell me what f of left of x is, it's already accounting for, so it says, look at this left of x value, and then look at the corresponding y value, right? But that corresponding y value gives me the accumulation from 0 to this x value.
But for the first one, say it was in the third interval, how does it know to switch to the second interval?
It doesn't have to switch. So that's the thing, right? So when we think about our accumulation function, so let's remind ourselves, the accumulation function, f of x, tells me the accumulated area as the side length goes from 0 to x. So when I say give me the accumulation of left of x, I'm saying give me the total accumulation that's happened as I go from 0 to left of x. So 0 to left of x is all of the complete intervals. They're all encapsulated, right, from 0 to that endpoint. And then give me the accumulation from there. Okay. Yeah, well, it keeps graphing because I could have different, current values of x. Okay. We can talk more. Okay. So, all right. So, but thinking about the big picture again, right? We've developed this. We found the average rates of change for the given intervals. We use those rates of change to write our linear function. Whoops. To write our linear, stop being there. I want to be up here. Sorry. So we get this piecewise linear function that approximates our accumulation. Okay. Notice that we already did the hard work to get the rates of change. In order to write our approximate accumulation function, we had to already compute the rates of change. So the order feels a little bit sloppy. It should feel a little bit muddled because we actually do the find your approximate rate of change function sort of like as an intermediate step to write our approximate accumulation function. Does that make sense? Okay, so that's why I said in number 4, we've already done the work to find the corresponding approximate rate of change function, because we had to find the approximate rates in order to write the approximate accumulation function, the piecewise linear pieces, right? Okay. How are we doing? I'm getting hot. You guys, are we doing okay? I'm not getting much feedback, so can't tell. I feel like I'm on the fire. How are we doing? Yeah? Okay. So then at the end of the day, okay, so let's think about this. So what did we do? We had our blue exact accumulation function. We approximated it with these red linear pieces. We said, oh, hey, I already did the hard work to find the rates. So here are the corresponding rates that we had to find in order to find the rates of change for each of these linear pieces. Okay? And then what do I want to do? I want to make these approximations better. So as always, I let delta x get really, really small. And you can see on the right pane that the red graph is practically identical to the blue graph at this point. Like it's looking really good. And the approximate rates in the left pane are getting really, looking pretty good too, to a point where this looks a lot like just a curve of a function that I might be able to identify. Okay. And so these approximations get so good that they're as good as the exact rate of change. Okay. And so today we're going to start trying to figure out how we can encode this process mathematically. Question? Do you mean like when I look at all of the little pieces as they get close together that I end up with something that looks like this? Yeah, that's totally possible, and that will happen. Yes. It is, in fact, a property of the function that we're looking at, that this ended up being a linear rate of change function. Notice it's not a constant rate of change function, right? This is still a changing rate of change, because depending on what x value I put in, right, I get a different, the rate of change here is different than it is over here, right? So this is not a constant rate of change function. This is a changing rate of change function that happens to be linear. Okay? Okay. So did you all fill out 1 through 5 while we were doing this? Okay. So let's recap. So we partitioned the x-axis by choosing values for A, your starting value, and delta x. We compute we've been calling it the average rate of change for each interval by saying that R of x is equal to f of, let's go ahead and use this one, f of x plus delta x minus f of x over delta x. This allows us to write a so that'll go in the second blank in number 3. An approximate accumulation function that is piecewise linear. But in doing so, we've already done the work to find the corresponding approximate rate of change function. To make our approximations better, we change delta x to become sufficiently small. This yields an exact rate of change function. Okay. All right, so that is the big picture. Now, this whole time I keep saying this thing about let's make delta x get really, really small. It's time to make that idea a little bit more precise, okay? And so I want you to take a second to think about, quickly, because I've taken a lot of time already, to think about the idea of a limit. So you guys have heard in everyday life this word a lot, okay? So what are some things that come to mind when you hear limit? Speed limit, right? Okay, what else? A what? What limit? Death? Debt. Oh, I was like, okay, a debt limit. Okay. Let's not go there. Okay, so, all right. So there are things that you have in your life that you might think about with limits. So here's a word of warning. There are times in mathematics where your daily experience will help you understand a concept. And then there are times in mathematics when your daily understanding of a word will hinder your mathematical understanding, okay? And this is a case where, for instance, speed limit is not the way you want to think about a limit, okay? A speed limit is basically what we call in mathematics an upper bound, okay? You're not supposed to go past it, okay? But that does not encapsulate what we think about mathematically as a limit, okay? So what I want to talk about is what mathematical idea of limit that we want to use for our purposes, okay? And so the way that I'm going to do this, this is not the big picture, right? Continue taking mathematics and you will continue to develop your idea of limit. Okay, but for our purposes, this is the way that I want us to think about it, okay? So limit in mathematics, 2 representations of the same number. So let's ignore that title for a second and just think, okay? So if I take the symbols A and B and I say that they represent different real numbers, then it is always possible to find a number between them, such as their arithmetic mean, A plus B over 2, okay, which is the number halfway between A and B. Do you agree or disagree with this statement? Agree? Okay. Keep that in your brain, okay? So what did we just say? If they represent 2 different numbers, then I can always find something in between them. So if A and B each represent a real number and it is impossible to find a number in between them, then A and B must represent the same real number. Agree or disagree? Okay, so if we believed in the first one, then we really should believe in the second one, right? Okay. Keep that in mind. 0.99999 repeating represents a number, a real number, right? These 9s go on forever. Agreed? can you find a number in between 0.999999 repeating forever and the number 1? So some people answered fast. Does everybody agree, though? Do you need a second to think about that? So there's no way of finding a decimal representation of a number that would shove in between 0.9 repeating forever and 1, which according to our second statement means that 0.999 repeating forever and 1 are in fact the same. Okay? This is pretty cool stuff. Okay? So when we talk about limits, what we're going to be talking about is how we can represent two things that are the same in different ways. Okay, that's essentially what we're getting at. And we're really going to concentrate on this idea of, can we fit something in between? And if not, then these two things, these two representations are in fact the same. Okay, so let's, oh, and here's a notation for that. So I'm going to keep talking about the notation. So don't stress yourself too much about it at the moment, but this is something that all of your other friends in calculus probably saw in the first week, but we're cooler than them, so we're seeing it now. So this lim is just to say limit, okay? And then what I've done here is represented this decimal expression as an infinite sum, or well, it's not infinite, it's finite, but then we make it infinite, of all of the decimals. Don't worry about it. We'll come back. Okay. All right, so, oh, I didn't want to do that yet. Okay, so we have this on the back side of your handout. We're going to do it now. Okay, so what we've had is this function, this a of x function, and we tried to, or we did come up with a formula to represent the average rate of change of this function over a given interval. Okay, so so let's actually work with that a little bit. Okay, so we had a of x equals x. Ooh, that was exciting. Equals x squared. Okay, and I want the average rate of change for this function over the interval x to x plus delta x. Okay, so how can I represent that symbolically? So I want average rate of change over this interval. Vishay? That was the point. Yep. So we had this way of computing the rate of change of a function, okay, over an interval, and we said that it was that function's value at the right endpoint of the interval. Okay, now our function isn't called f. Our function is called a. So I'm going to write a of x plus delta x minus a of x. So this is our change in outputs relative to our change in input, right? Whoops. This is still a very general statement. Okay, so this is nothing more than applying our statement about how we find average rate of change over an interval to the function a. Okay, but the cool thing is I have the rule for a. So what I want to see now is, can I create an expression that's equivalent to this, that's sort of simpler and easier to wrap my brain around? Okay. In particular, when I write a of x plus delta x, what is that? X plus delta x squared. Great. Oh, I just jumped a bullet. So a of x plus delta x is x plus delta x squared, right? And a of x is x squared. And then if I simplify the denominator, I just end up with delta x. Can I simplify this further? Some people said yes. So how would I go about trying to simplify this? So I could actually square this, right? When I square the quantity x plus delta x, what do I get? Is it x squared plus delta x squared? Plus x times delta x plus math. FOIL method. Okay, so you keep distributing, right? You end up with this. Okay. Now we could, so this is an expansion of the first term in this expression. Okay. But notice that we now have some like terms that we can subtract x squared minus x squared. The remaining terms both have a delta x in them. So I can factor out a delta x. And I get this expression. That is 2x plus delta x. And then delta x divided by delta x is just 1, right? So then we're left with the 2x plus delta x, okay? So this is my average rate of change function. Okay, nice and simple and pretty looking. Okay, now I'd like to point out that I haven't taken a limit yet. So for those of you who have taken calculus, you're probably anticipating what's happening next, okay? I want to remind you that we are not in your old calculus class. So if I ask you to tell me what the average rate of change is, this is what you should give me. You should not let delta x go to 0, right? So make sure that you're not thinking in terms of your old class. Make sure you're paying close attention to the questions that I'm asking and what I'm looking for, okay? Now, question? We'll talk about limit notation soon, but we're not there yet. Hopefully in the next 4 minutes we'll get there. Okay, so this is the notation that I'm introducing, okay? So when delta x gets really, really small, this expression is essentially the same as 2x. Okay, so I've got this equal symbol with a dot over it. Okay, you'll probably see this if you take a physics class. Okay. So for sufficiently small values of delta x, this 2x plus delta x is essentially equal to 2x. Okay, and what do I mean by this is essentially equal to? I mean that if I were to pick a value for x and compare the value of 2x plus delta x, or sorry, I didn't mean to say that. I meant to say if I were to compare the value of this expression and what I get when I plug in my value into 2x, that they're basically good enough. And by basically good enough, that means I could find a delta x that's even smaller that would make it so that, I'm saying this badly. Let's do the activity and it'll become clear. Okay, so when x is 5, I've asked you to do two things. I said compare the value of this expression that I've got this star down here next to, okay, and the value of 2x. Okay, when x is 5, what is 2x? Not a trick question. 10. Okay. Cool. Okay, this expression, okay, we just did a whole lot of algebra that tells us that it simplifies nicely to 2x plus delta x, right? So I don't even have to work that hard to figure out what this expression is. I just have to plug in 5 and delta x into here, and it'll tell me what that value is. So what do I end up getting? 10.01. Okay. Now what happens if I change delta x so that it's 0.001? What changes? Is 2x still the same? Yes. Does this expression change? Well, the value of the expression. Oh, that was really good. You guys are paying attention to my words. Cool. So the value of the expression does change, and it becomes 10.001. Okay. So how do I relate this to the idea of limit? Well, I want you to now think of a number in between this value and this value. Give me a number. What's a number in between? 10.00011. Okay. So this number falls in between these two values. Okay. In order to say that 2x plus delta x is essentially equal to 2x, I should be able to find a value of delta x that's small enough to where this number is no longer in between the value of this expression and the value of this expression. So can you give me a delta x that would now exclude this circled number from the range between here and here? So this is going to change, right? Because I'm going to pick a new value for delta x. Can you think of a delta x that would work? 0.000.
Do you like this?
0.01. You want another 0 for kicks and giggles? Okay, so if I put another 0 there, then the value of this expression becomes 10.0000001. This number is no longer in between 10 and this number, right? So the value of this expression I can control, and when I make delta x small enough, I can make the value of this expression be essentially equal to the value of this expression. Okay? Just so that you have an idea of where we're going with this. I'm going to come back and do this, but all of this builds into an idea that we call the derivative. Okay? And so that's where we're going. It takes a while to get there. We will get there. Great, thank you.